All right, so here we go. Let's talk about this. The density of a material is defined at a point is defined as the rate of change of mass with respect to volume. So when you thought about density in the past, did you think about it as a rate of change? Well, it is. A density is a type of rate of change. Okay? It's the rate of change of, if it's material, mass with respect to volume. So therefore, what would it mean to say that the density of a concrete block at a point in its interior is 67 grams per centimeter cubed? So this is to assess if you've learned something profound about rate of change so far this semester. So why don't you have a conversation for a minute or two and see if you can apply what you've learned about rate of change to this situation. What would it mean to say that the density of a concrete block at a point is 67 grams per centimeter cubed? Go. What would that mean? Okay, so we want kind of the strongest, the most robust, or the best definition of what it means that some material has a density at a certain point of 67 grams per centimeter cubed. Joseph.
Okay, at that certain point, the density is changing at 67 grams per centimeter cubed.
Okay. Well, changing with no, it doesn't have to be changing. It doesn't have to be changing. Yes, sir. Okay. So what does that mean? Okay. Something about anywhere around it. Something about anywhere around it. Other possibilities? Yes, sir. Okay, but what does that? We're saying, what does that mean? So to say that the rate of change is 67, what does that mean? Yeah.
In any area of centimeters cubed, there's 67 grams of concrete.
So for any volume of centimeters cubed, any volume, there's 67 grams of concrete. What do you think about that? Okay. Yes, sir. Okay, so this is true. Given us 1 centimeter cubed, there's going to be 67 grams of concrete. Would you agree with that? Okay, but this says a whole lot more than that. That's a true statement, but that's a very narrow view of what it means to have a rate of change of 67 grams per centimeter cubed. How do we open that up and let it be a lot more broad? Yeah.
For every cubic centimeter you add,
Okay.
you add 67 grams.
Yeah. Okay, it's true, but it's still kind of saying the same thing. That if you have 1 centimeter cubed, you get 67 grams. Yes, sir.
For every centimeter cubed you have, increase at a rate of 67 grams.
Can someone give an answer that does not involve one?
Okay, I got it. Thanks. Who's next? Yeah.
So for any volume that you have the rate of that.
Right, and what does the rate mean? What does the rate mean? So let me... Try again. Talk again. This is how you want to start. For any given something, tell me what 67 grams per centimeter cubed means. Go. Okay, someone want to try now? For any given... Joseph.
For any given volume,
Okay.
the rate of change is 67
But what is the rate of change? What is the rate of change?
around that moment.
Okay.
Around that.
Yes, sir.
For any given time, the rate of change is going to be 67 grams per centimeter cubed.
But what does this number 67 grams per centimeter cubed mean? What does it mean? Yeah, what does it mean? What does the rate of change mean? Yes.
For every given change in cubic centimeters.
Okay, hold on. For any given, you got it. For any given change in cubic centimeters, yep.
The mass will change by a factor of 67.
Right, we'll change 67 times as much as the change in centimeter cubed. What is that in essence? What is that? What is that saying? Mathematically. dy equals mdx. For any given change in volume, your mass will change 67 times as much as that change in volume. So that's a lot broader statement than just every 1 centimeter cubed is 67 grams. What about if it's 0.1 centimeter cubed? Then how many grams do you have? If you have 0.1 centimeter cubed, how much mass do you have? 6.7 grams. If you have 10 centimeters cubed, how much mass do you have? 670. Do you see? So, this is the most robust, the strongest, the broadest, the best way to think about rate of change. That for any change in your independent, your change in your dependent will be that many times as much as your change in the independent. Okay? So it's not just about, like Cerny was prompting, it's not just about 1 centimeter cube. It's about any amount of volume that your change in mass will be 67 times that change in volume. dy equals mdx. Okay? Yes. Okay. Okay, so here's an example. A concrete beam is painted on one end. It has a, if you slice it perpendicular to the length of the beam, you get a uniform density. But down the length of the beam, the density changes. Okay? So the beam is 10 meters long, has a cross section of 12 by 5 centimeters. And here's a function for the density. Okay, there's the function of the density as a function of the distance in meters from the painted end. Distance in meters from the painted end. Okay? So, what kind of function is that? It outputs density for distance from the painted end. So what kind of function do we have? Rate of change. And so and I've definitely given you a prompt there by using this notation that they use in the book, the R sub m, right? So rate of change of mass. Rate of change of mass with respect to volume. Okay? But that's as a function of the distance down the beam. Okay? All right, so define a function that gives the mass of the concrete beam as a function of the distance from its painted end. Okay? Display graphs of density, display the graphs of the density and mass functions. Okay? So what is this? This is, it gives the density or the rate of change of mass with respect to volume as a function of distance down the beam. So now we want to define a function that gives the mass of concrete as a function of the distance from its painted end. Okay? Display the graphs of density and mass functions. You got a little work to do here. See if you can do it. Work together. Okay? Go. Okay. Okay, so how are we going to set up a mass function? We have the rate function of mass with respect to volume, and we want to set up, how are we going to do this? In general. So what will the structure, the overall structure of that function look like? How will we get an overall structure of a function that's going to give us mass now that we have rate of change of mass? Oh, please know this. Yes, sir.
Integral of from 0 to x of that rate.
Okay. So let's call it, we're going to call it m. This is going to be the mass function, right? So mass with respect to distance down the beam. And so this is the whole deal. So for a month we've been working on. You know how fast a quantity is changing every moment? You want to know how much of it you have every moment. Okay? And we did all this hard work of going from exact rate to approximate accumulation to exact accumulation, right? We went through this whole process and we did a lot of work, and because we did all that heavy lifting and hard work, we earned the right to take the fast track from exact rate straight to exact accumulation. And the key to that is integral. Integral is now taking us straight from exact rate to exact accumulation. Okay, so Control-Shift-I. Control-Shift-I. There we go. And so we're going to integrate from what to what? We want a mass function as a function of distance from 0 to. It's a function of distance from the painted end. D. Okay? What is our rate function? R. So I could copy and paste the rule. I could put the rule in there, or I could put that in there. So R sub M, Control 9. And so what about this? Is it D? Need something different, right? We need something that represents every moment, starting at 0 to wherever we're stopped accumulating D. Okay? We don't want the rate only at the end, D, to be a constant rate. We want this rate function at every moment from 0 to D. We need a new variable because of that. So let's use X is fine. Okay, so we'll use X. Okay, so then what does X represent? So the input into the rate is what kind of thing? What kind of thing? Is it centimeters cubed? Is it grams? What is it? No. No. What's the input into the rate function? D. What does D stand for? Distance in meters, right? So therefore dx has what unit? What does dx mean? change in meters. So if I have grams per centimeter cubed as a rate at a moment, and I multiply by a change in meters, is that going to give me a little bit of mass? We've got some unit problems here, right? This is what? This is it's the density at a moment, which is going to be, the units of that are grams per centimeter cubed. The output of the rate function is grams per centimeter cubed. And a change of x is what? Meters. But I know that momentary rate times the change is needs to give me what? Grams, a little bit of grams, right? A little addition of grams is what the product of those two needs to give me. A little amount of accumulation, which is grams. So what's going on here? How do we need to fix this? Why? So grams per centimeter cube is the density per centimeter cube. We can't do that times a change in distance down the thing to get grams. So how do we need to take, what's that?
You have to multiply by the volume
You have to multiply by the volume
to single out the grams.
to single out the grams. Okay? So I definitely want meters here. Okay, I definitely want to keep the dx as meters because that's the unit on the independent variable. So I need to adjust this rate function so that it's correct. So what information haven't we used that we're going to have to use here to get what's inside that integral correct? Yeah. Divide by 100.
Divide the rate function by
Well, there's more to it than that. So what are we not using? So this is grams per centimeter cubed, and then this is only just distance down the beam. So what is the missing link here that we're not talking about? The cross-sectional area, right? The cross-sectional area. We're gonna need to bring that into it, right? So if it's grams per centimeter cubed, we really need this in the end to be what? Grams per meter. So how we're going to get this whole thing to be grams per meter? So we're going to multiply by our cross section. That in let's see. So we can multiply. So if we got r sub m x, if we multiply by 12 and multiply by 5. Right, so we're trying to get just the rate per distance now. Instead of the rate per volume, we're changing it into a rate per distance down the beam. So if this was grams per centimeter cubed, and this is centimeters, and this is centimeters, now what do we have? Now what unit do we have? Grams per centimeter. But we need it to be grams per meter because this dx is in meters. Right? dx is in meters, so we need grams per meter, and I think that's the first suggestion. How do we get grams per meter? Divide by 100 or multiply by 100? If you have this many grams in 1 centimeter, how many grams do you have in a meter? 100 times as much or 1/100th? I have this many grams in a centimeter. How many grams would that translate to in a meter? 100 times as much or 1/100th? 100 times as much, right? If I have so many grams in a centimeter, then in a meter I'm going to have 100 times as much mass. So I'm going to need 100 too. Okay, so now that whole thing now gives me grams per meter down the beam. Now we've changed that rate. That whole thing now is the rate of how the mass changes per meter down the beam. Did you catch it? So what do we need in here? We need 100 times 12 times 5. And now everything that's the dx is per meter is a change in meters, and then 100 times 12 times 5 r is grams per meter. That's the rate of change as grams per meter. Because I basically took the density and multiplied it by the area, and so that it gives me grams just per distance. Is it okay? I did, that was my very best. That's the best I could do explaining that. Did you track it? Figure it out? Okay, so now we want to graph both of these. So if I want to graph the rate on the left, I'm going to do y equals this one, but with x, and I want it from what to what? The beam is 10 meters long, okay? And then I'm going to graph on the right side, use apostrophes, okay? I'm going to graph this one. But I want to graph it, so x, and then x apostrophe, and then 0 is less than x apostrophe is less than 10. So let's graph it and see how we did. So you got to get your scale right. Here's the rate function, okay? But actually, don't we want to, so if we want to graph do we want to graph this rate? So this is the original rate function of mass per volume. So do we want to graph that one, or do we want to graph the one we actually find the integral of? The mass per distance down the beam. I think probably that one. We want to graph the rate of change of mass of distance down the beam. 100 times 12 times 5. What's happening here? Where's my rate function? Curve is outside the region shown. What did I do wrong?
It is extremely high.
More than this?
Wait, that one?
The rate function is extremely high?
Wait, no, not the rate function.
That's not the word. I'm not seeing the rate function. That's what I don't understand. Where's the rate function? Okay, so we got that. Where's the rate function? I don't know. Where is it? Didn't come. Yours came up? Let me just try typing it in again. Yeah, please. Not when it's multiplied by 100 times 12 times 5. Maybe I am still too small. Yep, I was too small still. So this is grams. So here's the deal. We've got a 10-meter beam, and we're talking about grams. That's why these grams per meter and total grams is going to be big numbers, right? Kilograms might be a more appropriate unit. We can just transfer that at the end. But the reason these quantities are so large on the y-axis is because grams are really small compared to a 10-meter beam, right? Okay, so we got it. So this is the rate of change of grams per distance down the beam now. This is no longer pure per volume centimeter cubed, but per distance down the beam. And then here is our total, this is our integral function. So I got some questions for you. So, just happened to get 6, huh? So it says click on a point. I will give you the point here. So the point I have is x equals 7.34 and y equals 2.97 times 10 to the 6th. Okay, so there's the coordinates. Okay, now you're going to interpret the coordinates in terms of the beam's mass and in terms of r. Okay, and then you're going to answer these two questions. What's the beam's mass that's made by a segment from 2 to 5 feet from its painted end? Express it in two ways and find the value. And then think about how you would answer this third question. We need to mark the place on the beam where 50% of its mass is on either side of the mark. Where should we place the mark? And then you're allowed to answer that in any way that you could think of, okay? Any way that you would be able to answer that third question is fair game, okay? So you got a little work to do here. Work together. If you've got a question as to what just happened in the last 15 minutes, get that question answered as well, okay? So Cerny can roll around. You can ask each other, but get yourself up to speed if you got lost somewhere, and then if not, work on these three questions. Go. Cerny, are you able to walk around? Okay. When you can. Thanks.
I deleted and checked there was control 9 for function notation, and it won't graph even the rate function.
Did you go way out on the y-axis the way I have it?
No, because it doesn't say graph is outside the region, so it says I cannot graph a curve of this type. Can you show that?
Yeah.
Use control 9 every time. It looks right. So you could just try starting over. So like
I did.
delete out the blue graph, and just type it in again. 100 times 12. Yeah, that's all I can suggest. It looks right to me. There's some little syntax thing.
All right.
Sorry, I don't know. What'd you say? Sorry, I don't know what to tell you. I think so. Are you just graphing r sub m, or are you graphing 100 times 12 times 5 r sub m? I'm graphing 100 times 12 times 5 r sub m, the thing that we're integrating. Yeah. I'm graphing the grams per meter, not the grams per centimeter cubed. Grams per meter. Did you put parentheses around all this, everything that I have? You got it? Can I scroll back? Okay. So coordinates. I got these coordinates: 7.34, 2.97 times 10 to the 6th. What does that point mean? What do those numbers mean? Somebody new? Who thinks they can tell me? Can you tell me? Yeah. I forgot your name. Sean. Can you tell me what those coordinates mean? X equals 7.34 on this point right here. And y equals 2.97 times 10 to the 6th. Not sure. How about next to him? What's your name? Jansen? Chance. What is the meaning of the point? Oh no. Okay, here you go. Yeah, no, you raise your hand.
At length, 7.34 feet, its mass is 2.9 times 10 to the 6 grams.
Okay, so first of all, so at 7.34 meters, you said the mass is this. That's unclear. What do you mean? What mass is this? See? I don't know why that's happening though. Yeah, because you know, Windows doesn't have any bugs in it. No.
No. This thing is rare.
Okay. Anyone want to give it? What mass are we talking about? Yes, it is a number of grams. What's that? The mass, that is not, no, it's not the mass of the concrete beam. What is this function telling us? If you put in 7.34 meters, you get a mass. What mass is that? Yeah. The accumulated mass from the painted end. It's all the mass that's been accumulated, or from 0, the painted end, to 7.34 meters, right? Accumulation, the mass is accumulating as you move down the beam. So it's the mass of the first 7.34 meters. Okay, next question. How do we express the beam's mass starting from 2 feet to ending at 5 feet? Two different ways that we can do that. Okay, so I'll just tell you. Gosh. All right, let's just do top hat. Two questions, one answer each. One answer each. They are open.